Yeah, so this work is some new work. As Stephen said, I primarily been a terrestrial geophysicist, but my interest in subduction zones has driven me offshore, in large part because to really understand the behavior of megathrust earthquakes, and particularly the components of megathrust earthquakes that are capable of creating large tsunamis occur way offshore and very difficult, if not impossible, to understand using land-based techniques, at least for most of the world. And so I am going to be talking about extending GNSS acoustic based seafloor geodesy. So this is very similar to GPS on land in the late 80s and early 90s, where we're using a lot of heavy equipment to make individual data points that we repeat surveys year over year to get long-term displacement that we can use to derive strain fields or locking on megathrust faults or the likes. Okay, so I'll talk a little bit about the technology, a little bit about what we've done for getting some instruments funded, a community experiment very briefly, and then where we're pushing things way off into the deep end. Okay, so to start off, in order to understand near trench, as I said, we actually need to get near trench with our observations. And so what I'm showing here on the left-hand side, you can see my pointer. I'm hoping sometimes I can turn on the laser, but not always.
Yeah, it looks good. We can see it.
Okay, I think that might be a little bit better. Okay, so what I'm showing is a number of different subduction zones and their approximate orientation of the trench relative to them. So this is Antofagasta, Chile versus Cascade Range in the Western United States, Kenai Peninsula off of Alaska. I'm sorry, this is Sendai region of Japan and Kenai Peninsula off of Alaska. And so you can see we're even at the closest approach of these characteristic subduction zones, we're at 100 kilometers from a trench, and then it's marching further and further away. And in all of those cases, either inferred from large earthquakes or from locking models, the real behavior is occurring offshore. So one way to evaluate this to really characterize the need is to look at how well we can resolve using land-based data versus if we had data to the seafloor. And so I did these very simplified 3D models down below and 2D models in cross-section, evaluations of how well we can resolve patches on the subduction interface, giving sort of, I did basically kilometer by kilometer steps of GPS type instruments with horizontal and vertical capabilities from the trench versus looking at nearest approaches to the trench much further away. And so you get perfect resolution if you have geodetic data all the way at the trench, mapping out fault blocks that are on the order of 10 to 20 kilometers. And you can see this very clearly in what we see as what we call checkerboard tests, where you create a synthetic models of ones and zeros for displacements, and then you predict the deformation on the surface. You add a realistic noise to the models, and then you try and reinvert. And so we get these checkerboards really well at the surface. We always lose capabilities at depth, and that's just because even with perfect land-based observations, we are further and further away from the faults as it dips deeper. Okay, but if you step back 150, which is kind of the Cascade example, you'll see that we only get that really near trench component. And even worse yet, and this is a really unfortunate, is you start to see features offshore. And I see an unfortunate frequency for papers to be published with these null space sort of hallucinations that generally are not interpreted by the authors, but are very frequently interpreted by the community that are not experts. So it's one thing that we have to be pretty careful of. But long story short, with on-land data, your resolution offshore goes to zero really quickly. Okay, so I am going to give a quick intro into a method, one of two primary methods for doing GNSS acoustic. This is what we'll call the Scripps method, which was first developed by Fred Spiess way back in the 80s, but really further improved by Dave Chadwell. In this method, what we do is we use a triad of three transponders that we put on the seafloor. So this is a two-dimensionalized version, only showing two. So I'll put the triad in there. So you can imagine a third one going off in space. The spacing of those is about 0.9 water depths from the center. It ends up being about 1.56 between water depths between any of these stations. And we want to minimize the difference in water depth across those transponders, which I'll talk more about in a second. They're deployed nowadays on these reusable benchmarks that use little titanium connectors. With the reusable ones, we can drop them off the ship for an initial deployment, but we can replace the transponder with a new one with millimeter level precision, which is really fantastic if we want to get extremely long-term observations. From the surface, we have a vessel. It was originally these large Unals-based vessels, which are extremely expensive. They operate at about $50,000 US a day, depending on ship. But on the vessel, we have dual GNSS. We incorporate accelerometers, gyroscopes, magnetometers where they're available. For when we use all this information for positioning and inertial navigation. So we know where we are in space and then how the vessel is rocking back and forth relative to, and we don't show it here, submerged is a transducer that's frequency matched with the transponders that are just doing acoustic pinging to get two-way travel times between, from that centroid to each of the three individual transponders. We hold it very near the centroid, but we'll talk about particularly our new method that we use with using these small wave gliders can't stay still, so we send it on a small square path, about 50 meters in characteristic length. As long as the seas are in favor and we have enough solar power to operate these things, we generally want to collect 2 to 3 days of 24-hour data to get centimeter level positions at that centroid. And then we can repeat that, annually is the preferred, but in some cases you can do it more frequently, as Japan is doing, using a slightly different method, or less frequently if ship or funding only allow such. So, working with Scripps, there's a large team, again, led by Dave Chadwell, who really developed this new method using these really low-cost wave gliders, which I'll show more in the next slide. We were able to go back to the National Science Foundation and argue very strongly that we need to develop this instrument pool for NSF-funded science. And so we were able to get what we call the SCIP, the Seafloor Geodetic Instrument Pool, that included 51 acoustic transponders. These things have 10-year battery lives. They're rated at 3,000-meter water depth. They have one in every three of them have an absolute pressure gauge that gives us sort of short-term centimeter vertical motions, whereas the acoustic transponders themselves are capable, as I said before, about centimeter level, and our method only gets horizontal for that. And then also the purchase of 3 wave gliders that are equipped with the full GPS and acoustic positioning hardware for making our observations. These wave gliders, as I mentioned, are autonomous or semi-autonomous green-powered surface vehicles. They run all their electronics off of solar panels, as you can see here, and their locomotion is driven entirely by differential vertical heights of wind-driven waterways, where the maximum height at the surface, and we fall off right to essentially zero as we go to the wave base. So these wave gliders have, it says 7 meters. The newer ones have an 8-meter, what we call umbilical, that attaches the surface float, what I call the surfboard, attached to fins at the seafloor. So every time the water goes up, it pulls the umbilical forward. The little fins launch it forward. The fins then rotate backward, and when it goes back down, it launches forward again. Capable of locomotion at about 2 knots as long as you have, even moderate sea states. as I said, these things are autonomous. They're really autonomous. We call them semi-autonomous because we do pay for programming and piloting for the vehicles, particularly for avoidance. So if there's a large vessel nearby, they'll go and move it out of the way. And they also watch weather conditions and put it in low power mode if we have to wait out a particularly bad storm. So that costs about $700 a day, which is just a drop in the bucket. You can imagine compared to that $50,000 a day that we were paying for Noah's vessel. The ones that we got funded, these three waveguiders have 6 kilometer ranging and the transducers frequency fixed with the transponders we've got as part of the instrument pool. Okay, I'd mentioned before that we want to have those transponders at approximately the same water depth. I'll have a little bit more of that later in the talk, but we normally say that we want to have them less than about 100 meters differential. And that spacing between transponders, we say is about 1.56 water depth itself apart. And so I went through and did this large sort of evaluation of a couple of different subduction environments to evaluate what's capable. This shows a little bit about the methodology. We take the seafloor bathymetry. I'll calculate what I call a scaled gradient, which scales the seafloor by the water depth at that position. And with that, we get a height parameter that we can measure. That is that over that for that water depth, where are we, what is the gradient across that section? And so what we're looking for is values less than 100 meters. And what we find, this is off Antofagasta, Chile. Anything that's in the blue zone here is viable. Anything that's in the red zone is not viable. And what you can see is that large portions of the subduction zone, and I don't have it mapped out here, but the trench too, nothing at all near the trench is viable. And this is really the condition for most subduction zones worldwide, is that we have very steep gradients in excess in many places of 10%. There's another limit. I mean, so even if you're in shallow water, there's some places where gradients are pretty easy, but there's other places where you have to do a little bit of trickery. So I was going to mention very briefly, in part because we've got the instrument pool funded before COVID and nothing was happening for a little bit within COVID, we were able to get a community experiment ran to install stations, much of that pool in two big experiments off of both Cascadia and Alaska. And so these red bullets are those Alaskan ones that are trying to answer a bunch of different scientific questions, but we really are funded to make those measurements and get the software ready and do some community training. We're not doing much with the science directly. Or I should say funded. Everybody's working with the science. But when we make those triad positioning, you can see for a few of these sites, they're pretty easy. Sites like this, we need to find basins in order to get, something that works well. And then other places like the one measurement that we wanted to get on the incoming plate, because they're only rated to 3,000 meter water depth, we had to look for the few little places that are above 3,000 meters. And so that's what it's actually the colored contours here. So we found this on Chignook Seamount, but in order to get that, we had to basically place it at the edge of three different directions of slopes. And we were really grateful that the current in the ocean was not very fast, because we drop it off the side of the ship and we just wait for it to float down to the bottom at about a meter a second, a little bit less than that. So that was successful. Anyway, I'm going to come. So we are kind of limited in where we can go to get these spatially flat environments. I showed you that little example starting off in Chile. So it was the Antofagasta region. This is a larger region looking across a large swath of Chile. Sorry, Chile is now turned on its side, but you can see versus the trench, there's essentially no place that we can really go with that low gradient environment. Okay, so in order to get near the trench, there's a few things that we need to do. We need to be able to do deeper water deployments. So most places near trench environments are much greater than your average water depth. So, greater than 5-6 kilometers depth in many places, even though those might be really short components of the section. Once we go into deeper water, of course, you need to have pressure vessels that are tested for those higher pressures, but we also need to be able to do acoustic ranging at greater distances. And so in order to do that, we need to use lower frequencies. So the frequencies that we've gotten for the instrument pool, 19 to 34 kilohertz. In order to go deeper water depth, we're using a what's called a low frequency. This is low medium frequency. This is low frequency. But it's just shifted a little bit below, so it's between 14 and 19.5 kilohertz. But we also need to very importantly test the conditions for high gradient environments. We can't get away from that. Also, because we get very near the trench, we have capabilities to see very fast changes on the megathrust interface and also maybe consider evaluating things that are occurring internal to the upper plate. So we'd like to, if possible, get dense field of observations. Okay, so I propose this mesh GNSS acoustic design for dense observation for deep water environment. So we were funded a couple years ago for a 3-year test. This is not a science, but a methodological experiment at this point to test these lower frequency equipped wave glider with 10 transponders and a mesh design that go down to 6,000 meter water depth. We deployed in 2024 on the back of a cruise that was doing a deployment as part of our community experiment. We did a reoccupation last year, and we are planning another one for this summer. Okay, so let me really quickly point through the value of a mesh design. So right now, we use 3 transponders to get 1 centroid. So a characteristic design would have 9 transponders for 3 data points. So we can call that a 33% transponder efficiency. But you can imagine, once you add a 4th transponder, now you have 2 data points, okay? And so your efficiency is going up, okay? Once you make a hexagonal design like this, now you have 7 transponders and 6 data points. You're near 100% efficiency. You can also do some interesting things if you have the capabilities to measure large triads or these little diamond shapes structures to get even, what we call these secondary centroids. So with a theoretical design like this is just as an example that I used in the proposal. You can get 43 primary centroids and then 68 secondary centroids, all from 32 transponders. So we go from 33% efficiency up to over 300% efficiency. If you have the money to build such a large design and you really have the need for doing it at that level. But you can see as that grows, the efficiency grows substantially with it. Okay, so I made the proposal. We got new instrumentation for that. We got a new wave glider for that. So this is showing us preparing to leave Seward, Alaska. These darker orange instruments are the ones that are rated at 3,000 meter water depth. These lighter orange ones are 6,000 meter water depth transponders on those reusable benchmarks ready for deployment. Here are our 2 wave gliders. This is one that we bought as part of the community experiment. This is the brand new one. You can tell it's brand new because we use copper paint to limit biofouling, and it is still a pretty penny sort of color, pretty copper rather than oxidized. So once it goes in the water and comes back after a season, it's going to turn to this green oxidation state. Okay, so those are deployed in 2024. As I mentioned, we install these community sites along, mostly along places where we have big questions and earthquake behavior, and then we have one to get the incoming plate. And that's a large part because the closest other place where we're measuring the modern deformation rate or plate rate for a Pacific plate is down in Hawaii. So this gives us a local observation. So even though I was funded purely for a methodological experiment, we were going out very near the trench out here, and it's a perfect place for me scientifically to do this test. So what we did is we deployed it in the very near trench region of the 1946 tsunami earthquake. So this is the most extreme tsunami earthquake we've ever seen. Tsunami earthquake means it's an earthquake that's created a tsunami much larger than we expect given its magnitude. So this created locally 40 meter high tsunamis in Unimak Island. It was only a surface wave magnitude 7.3. event. It also created a large 10-meter high tsunami all the way down in Hilo, Hawaii. So this is an extreme tsunami for an earthquake its size. And a large part of what we understand its capability came from was very near trench rupture. So making these observations in that very near trench region will be ideal. Okay, there's just a blow up of that array into that center, but we also have two community sites measuring near their down dip limit. And you can see we also have some on land GPS sites that have given us some observations, including one for active Westall volcano. Okay, I had mentioned, oh, I'm running a little bit over. Okay, I'm gonna wrap up pretty quickly. That steep slope environment gives us, we generally say we need like less than 100 meters. That's 1 to 2% grade. We're down to 14% grade in our mesh network. The reason being is that very quickly we have unmapped sections of our horizontal velocity field. Um, Luckily, we did do CTD casts and we measured, at least during the deployment, our shallow and deep water sound speeds at that time. And while the shallow water sound speeds as we transected the region varied by up to 1.8 meters per second, the deep water was down to less than 0.02 meters per second. And so we have a 0.5 meters, I mean, a 5 millimeters change over 100 meters, it's gonna create a bias. But the fact that it's is really small, at least at that time, is really suggestive that it's really possible. Okay, I'm going to wrap up really quickly. This is our first year experiment results comparing our deep water versus shallow water. We're getting very similar repeatabilities, epoch by epoch, between our community sites and the deep water sites. This is just just deep water sites with our deepest water site going all the way down to 6,000-meter water depth right here, making this observation. We're getting very consistent repeatabilities through those. We can draw lines between two different data points over time now and start getting velocity fields. Um, they are extremely preliminary and they're all over the place. So this is really just the 1 sigma error for these, just so we can keep them on scale at this point. They seem to be all over the place. It's really way too short of a time to really evaluate it. But even with them being all over the place, if we collapse them down to a single value, average over a single value, we're getting something pretty close to the plate rate and plate direction, even in 1 year. So it looks like things are working well. We're really going to need to know more in the near term. So uh, long story short, with the mesh design, we have no inherent concerns of the geometry. The low frequency design seems to be working really well for repeatability. We need one more really a year to determine stability of sites. It's easy to draw a line between two data points. The third data point is really going to matter more. But it'll be extremely helpful to be able to make those measurements longer term so we can really start to get good science out of this. And of course, the efforts here will be useful for subduction zones worldwide, including planned efforts with SE4D.